What if the universe's most terrifying and profound secrets are nothing but a mathematical error? What if the darkest hearts of black holes, those cosmic monsters that swallow light whole, and the very moment of creation itself, the Big Bang, are not places of infinite mystery, but are instead fictions, glitches in the majestic code of Einstein's theory of relativity? This isn't just a tweak to a textbook. This is a fundamental rewiring of reality itself. The concept of a singularity, a point of infinite density where the laws of physics simply give up and die, has been the ultimate full stop in our understanding of the cosmos. It's the place where science, in its current form, must kneel and admit its ignorance. But imagine for a moment pulling back the curtain on that infinity. Imagine discovering that infinity is not a physical place you can reach, but a warning sign on a map that reads, "Here be dragons." Not because dragons, screaming that we have pushed a good theory far beyond its breaking point. Think of it like a divide by zero error on a calculator. The calculator doesn't show you an infinite result because infinity is real. It shows an error because the operation you asked it to perform is undefined within its limited framework. General relativity is our cosmic calculator, and when it tries to calculate the conditions of a completely collapsed star, it returns a divide by zero, a singularity. Our curiosity should not be about this error message, but about the hardware and software of the universe that doesn't produce this error. What is the universe's actual operating system? This line of questioning shatters passive acceptance and replaces it with a raging, insatiable need to know. It transforms black holes from terrifying end zones into laboratories, the most extreme ones imaginable, for testing the laws of quantum gravity. The event horizon is no longer a point of no return, but a veil, and we are desperately devising new instruments, both mathematical and eventually, perhaps observational, to see what lies behind it. The notion that singularities don't exist is the key that unlocks this veil, promising a revelation far stranger and more wonderful than mere infinity. The implications ripple outward instantly, touching the very nature of time and destiny. If there is no singularity, then what happens to something that falls into a black hole? Our current story is final and grim. It is crushed out of existence, its information annihilated at the singular end. But if that endpoint is replaced by something physical, something with structure, then the journey doesn't end, it transforms. The object or the information that constituted it might be scrambled, preserved, transmuted, or even funneled somewhere else entirely. This isn't just science fiction, it's a necessary consequence of removing the infinity. It resolves the infamous black hole information paradox, a crisis in physics where the immutable laws of quantum mechanics, information cannot be destroyed, clash with the classical prediction of general relativity, information is destroyed at the singularity. By banishing the singularity, we're not just cleaning up a mathematical inconvenience, we're saving the logical consistency of the universe itself. The curiosity here is profound. Is the universe fundamentally paradoxical, or is it our understanding that is flawed? The bet that singularities don't exist is a bet on a universe that is consistent, computable, and ultimately knowable. This is the hook that has captured generations of physicists, the chance to heal a foundational crack in our understanding of reality. If singularities are illusions, then what reality lies beneath? The answer forces us to descend into the bizarre, counterintuitive, and wondrous realm of quantum physics. This is where the revolution begins. General relativity is a theory of the very large, the cosmic, the smooth geometry of space-time. But when matter is compressed to such insane densities, we enter the domain of the very small, where the rules are written by quantum mechanics. Here, the certainty of classical physics evaporates into a cloud of probabilities. The Heisenberg Uncertainty Principle dictates that you cannot simultaneously know both the exact position and momentum of a particle. This isn't a limitation of our measuring tools. It is a fundamental property of the universe. This inherent fuzziness acts as a cosmic insurance policy against the formation of a true singularity. You cannot crush an object to a perfect point of zero volume because its position would be perfectly defined, violating the core tenets of quantum theory. There is a smallest possible scale of fundamental graininess to space-time itself. This graininess is quantified by the Planck length, an almost unimaginably small scale, about 10 to the negative 35 meters, where the very concepts of space and distance as we know them cease to function. A singularity is by definition smaller than this. It's like trying to describe something smaller than a pixel on a screen. The question itself becomes meaningless. Therefore, the crushing gravity of a collapsed star doesn't create an infinity. Instead, it compresses matter until it reaches approximately the Planck density, a number that defies imagination, but it is a finite number. This is the core of the curiosity, replacing an unphysical infinity with an impossibly large yet quantifiable state of matter. This entity has been given names like a Planck star or a Gravastar, a gravitational vacuum star. It's not a point, but a region, a blazingly hot, unfathomably dense ball governed by the laws of quantum gravity. The pressure from these quantum effects would ultimately halt the collapse, creating a stable, ultra-dense object. The search for the precise nature of this object is the frontier. Is it a knot of space-time itself, a manifestation of higher dimensional strings vibrating at their maximum energy? The curiosity is no longer abstract. It becomes a technical, detailed investigation into the phase transitions of space-time.
This is the concept of the Big Bounce, a cornerstone of theories like loop quantum cosmology. In this model, our universe is just the latest cycle in an eternal, perhaps infinite series. A previous universe, perhaps similar to ours or wildly different, underwent a period of contraction. However, instead of crushing itself into an infinite singularity, it reached a maximum, finite density, triggered by those same quantum repulsive forces that stop black hole singularities. At this moment of ultimate compression, the quantum gravity effects became dominant and caused a tremendous rebound, a bounce that set off the expansion we see today as the Big Bang. The curiosity this induces is existential. It replaces a single, inexplicable creation event with a cyclic, potentially eternal process. We are forced to ask, what was the universe like before the bounce? Did the laws of physics remain the same? Was information, the essence of what existed, preserved through the transition? The idea of a cyclical cosmos is found in ancient philosophies, but now it emerges as a rigorous scientific possibility driven by the need to avoid a singularity. The non-existence of singularities is not an arcane mathematical detail. It is a paradigm shift that reverberates through philosophy, our place in the cosmos, and the very nature of knowability. If the universe has no true endpoints, no literal holes in the fabric of causality where physics and logic die, then we live in a cosmos that is fundamentally rational and comprehensible from end to end. This is a monumental statement. It suggests that with the correct theory, a complete theory of quantum gravity, there are no places or events that are inherently beyond the reach of scientific explanation. The universe is, in principle, fully knowable. This reinstates a powerful form of cosmic optimism that was challenged by the bleak finality of the singularity. This has direct implications for the far future and the fate of information, and by extension, for any concept of meaning or legacy in an impermanent universe. In a universe with singularities, information is ultimately doomed to be erased. But in a singularity-free cosmos, information is potentially eternal. The energy and matter that constitute a star, a planet, or a living being may be transformed through unimaginable processes, falling into a black hole, being scrambled at its Planck core, perhaps being re-emitted via Hawking radiation or in a white hole explosion. But it is never truly destroyed. The universe becomes a vast cosmic computer that conserves every bit of information. This touches on deep questions of identity and continuity. While the you, that is a conscious pattern, would be irrevocably lost, the fundamental constituents that made you would persist forever, to be rewoven into the future fabric of the cosmos. We are not just stardust, we are potentially eternal data in the cosmos's hard drive. Finally, this new vision invites a new cosmology of life and mind. If the universe is cyclical and eternal, the conditions for life may have arisen countless times before in previous cycles and may arise countless times again. Our universe's specific constants and laws might be just one permutation in an endless sequence. This dovetails with questions about the anthropic principle and the multiverse. Furthermore, the interior of a black hole, once a dead end, is now a realm of extreme physics. Could a sufficiently advanced civilization, mastering quantum gravity, ever hope to navigate or even utilize these environments? Could Planck cores be engines? Could white holes be gateways? While this veers into speculation, it underscores the central point. By removing the singularities, we replace the cosmic game over screen with a continue prompt. The universe becomes a place of endless transformation and potential, a story with no final punctuation. The ultimate curiosity is this: if we are brave enough to let go of the comforting finality of the singularity, we are rewarded with a cosmos of infinite, breathtaking possibility and the thrilling, unending human quest to understand it all.